Today we're going to start a new topic. We're going to talk about limits at infinity. So we're going to formally define what it means for the limit as x approaches infinity of some function f to exist and equal L. Okay? We want something resembling an epsilon delta definition for this. That's our goal. And then later in the video, we're going to see some examples of using this definition that we're going to develop to actually give some formal proofs. So let's begin by drawing a graph. Okay? Get some intuition going. So there's a graph of f of x, and as you can see, f is tending towards the value L as x gets larger and larger. Okay? As x tends to infinity, f of x tends to L, or at least it appears that way from the graph. Okay? What does it mean for this limit to exist and equal L? So if you think back to the regular epsilon delta definition, where x is approaching some finite value, what happened there was we could make f of x minus the limit arbitrarily small, less than epsilon for any positive epsilon, as long as we pick our x's sufficiently close to a. So here we have something similar, except this time we're not picking x's close to a, but we're picking x's larger and larger. Okay? So in order to formally define this, we're going to have a for all epsilon at the beginning. And then we need to sort of formally express what it means for x to be sufficiently large. And then once the x's are chosen sufficiently large, then we'd like to end off our statement, or our definition, with then f of x minus L is less than epsilon. Okay? So how do we express that stuff in the middle? If we look at the graph, we want to say that there is some point after which the function and the limit are pretty close together. The function lies within the epsilon window around L, the epsilon window as I drew here. Okay? On this particular graph, that point would be there. Okay? Now we can call it something. I'm going to call it capital N. And then after that point, as we choose x's that are larger than that point n, okay, and we feed them into the function, f of those x's is going to lie within the epsilon window around L. Okay? So that's what we want. For all epsilon, if this limit does in fact exist, we want there to exist a point n, after which all the x's subbed into f are going to give us this, f of x minus L less than epsilon. F of x will lie within the epsilon band around L. Okay? So for all epsilon greater than 0, there exists an n. Okay? Now I'm going to write there exists an n greater than 0 here, even though we don't really need this greater than 0 part. N could be greater than any positive number. It could be greater than 10, or it could be negative. I mean, it's possible, right, if we just shift this graph over. So as long as there exists some real value n, we're fine. The convention is to specify the greater than 0. Okay? And you'll see why in a minute. So for all epsilon, there exists an n greater than 0, such that I didn't space this out enough, such that whenever x is larger than n, we have f of x falling within the epsilon window around L. Okay? This is the formal epsilon-N definition for limits going off to infinity. Okay? So this is going to be taken to be our definition. Intuitively, it makes sense. On the graph, you see it in action. Okay? Let's actually use the definition to give a few formal proofs of limits. So for our first example, we're going to prove that the limit as x approaches infinity of 1 over x is equal to 0. Again, we may begin with the graph, just to visualize what's going on here. There's 1 over x. I'm not going to draw the negative branch because we don't need it. Okay? And we want to show that the limit as x approaches infinity of this guy is 0. Okay? So what does that mean? As x gets larger and larger, 1 over x gets closer and closer to 0. So for any epsilon window we pick around 0, let's say this is our epsilon window here. Okay, that's negative epsilon. This is epsilon. Okay? Draw our window here. I tilted it a bit. There we go. There we go. Okay? There's our epsilon window around 0. For any such epsilon, there exists a capital N value, okay, that's greater than 0, such that whenever x is larger than n, our function minus the limit is going to be less than epsilon. So our function is going to lie within the epsilon window here around 0. Okay? On the graph, where is that point n? Well, the smallest that n could possibly be is right over here. Okay? Right at this intersection point. At that point, such that when we feed it into the function, we get epsilon. Okay? After this point, the function keeps decreasing. It never hops over 0 and then dips below the negative epsilon line. So it's this point right here, okay, that we want to show exists. We see it exists on the graph, but we're going to formally do it in a sec. Okay? And now for any x you pick that comes after that point, 1 over x is going to be within the epsilon window. Okay? So what is n? N is the number such that 1 over n is equal to epsilon. This will be the maximum value of n that will work, or the minimum value of n that will work. Any n larger than this one will work as well. Okay, so the min value for n, well, you can sort of solve for it here. N is going to be just 1 over epsilon. Okay, that's the minimum value. So given an epsilon, we can pick n to be equal to 1 over epsilon, and then we know that this statement will be satisfied. Any x chosen larger than n, 1 over x is going to be less than 1 over, or is going to be less than epsilon. That much we know from the graph. Let's actually formally do the proof. Okay? So these infinity proofs begin just like any other limit proofs. So proof, we start with our 3 let statements. So let epsilon greater than 0 be given. The proof that follows will now work for all epsilon. Now we want to show that there's a specific value of n. Okay? So we're going to pick our n value, let n equal something. We already know what works, but we're going to derive it. Let n equal something, and let x greater than n be given. Okay? So same 3 lines that we're used to seeing from finite limits. N in this case is playing the role of delta. So n plays delta role. Okay? All right, let's keep going. We want to bound 1 over x minus 0. We want to do some algebra and then show that this thing is going to be less than epsilon at the end. Okay, so the first thing we can do is clean it up a bit. The 0 doesn't make any difference. And now we have an absolute value of 1 over x. Okay, so 1 over abs x. Now, if you notice, x is always positive. Why is x always positive? Well, x is larger than n, and n is positive. Okay? So because of that, we can now drop the absolute value. So this is just equal to 1 over x. Okay? And now, we're told that x is larger than n. So if you take the reciprocal of this inequality, we get that 1 over x is less than 1 over, right? You can just take 1 over both sides of this inequality, but we have to flip the sign. Okay? So 1 over x is going to be less than 1 over, okay? And this is by the given info, okay? Over here. And now we're ready to pick our value of n, all right? So at this point, we've replaced all of our x's in our statement here with a constant n, okay? This is equivalent to the point at which you've replaced all your x's with deltas in a standard epsilon delta proof. Okay? At that point, you're ready to choose your actual value of delta to make this business here less than epsilon. Here, similarly, we pick an n such that we're going to have epsilon in here. And as you can see, what value of n works? 1 over epsilon. So maybe I should erase this just to put everything on one line. If we pick n to be 1 over epsilon, here we're going to have 1 over epsilon. And that's going to be equal to epsilon. And the proof is going to be done. So we need our n to be equal to 1 over epsilon, in agreement with what we found there from the graph. Okay? Here we just deduce this algebraically. So again, where did these steps come from? The first one was just simple algebra. This one is because x is larger than n, which is larger than 0. Okay? This is by the given info, okay? Our supposition over here. And this we get to pick, okay? Our choice of n, okay? So this is one of the reasons why we have this convention, okay, that n is chosen to be greater than 0. Because we do want our x's to be positive, okay? If n is chosen to be greater than 0, then x is greater than 0, and we know that whenever we see an abs value of x somewhere, or some expression maybe containing x's that we know is positive for positive x's, then we can just drop the absolute value and not worry about that, okay? That's one of the reasons. So that's our proof. Let's do a slightly harder example, because this was too easy. So for a second example, let's prove that the limit as x approaches infinity of sine x over 3x plus 2 equals 0. First of all, why is this limit equal to 0? Sine x is bounded. It's always between -1 and 1. And 3x plus 2 gets larger and larger as x gets larger and larger. So here we're dividing a bounded value by something which gets huge. The answer tends to 0, okay, in the limit. So let's give a formal proof. Same 3 lines. Let epsilon greater than 0 be given. Let capital N equal something, okay? And let x be larger than n. And what we want to do is we want to show that sine x over 3x plus 2 minus 0 can be made less than epsilon. And we want to find a value of n in terms of epsilon, which makes that happen, okay? So here's the first thing you should do. You should forget about the 0. Okay, that's obvious enough. And we might as well put the abs value on top and on the bottom. So we're going to have abs sine x at the top and 3x plus 2 and abs at the bottom. Okay? Now, please do not be afraid of the sign. Here, in these limits that go off to infinity, sign terms are pretty easy to deal with, okay? Unlike finite limits. We know that sine x in absolute values is less than or equal to 1. So in fact, we can just replace this entire sign at the top with 1. Okay? It's almost like cheating. We've just simplified everything so much right there. We've gotten rid of the sign, replaced it with a 1. Now, the 3x plus 2 in absolute values, we can just disregard the absolute value here and put down the 3x plus 2 alone. Why? Because, again, x is larger than n, and n is larger than 0. Okay? So x is larger than 0, and 3x plus 2 is therefore also always larger than 2, actually. But it's always larger than 0. Okay? So there we go. We've just bounded this expression by 1 over 3x plus 2. Perfect. We can simplify this a little bit by forgetting about the 2. Okay? So this is less than 1 over 3x. Of course, we didn't have to do that. I mean, we could have done the n replacement right away in this step. But it helps if you forget about the 2. Get something a bit simpler. Okay? So 3x plus 2, 1 over 3x plus 2 is less than 1 over 3x. We've made the denominator smaller, which makes the whole thing bigger. And now, just like before, knowing that x is larger than n, we know that 1 over x is less than 1 over n. So we can simply replace the x now with an n, and we're going to have a less than sign. So this will be less than 1 over 3 times capital N. Now, at this point, we could set this business equal to epsilon and figure out what value of n we need. So if this were to equal epsilon, what value of n would we need to choose? 1 over 3 epsilon. Just flippity-flip these two, and then you can find your n value. So let's pick n to be 1 over 3 epsilon. Okay, there we go. And what you're going to have at this step is this. Okay? The 3's are going to cancel out, the epsilon will go upstairs, and we have epsilon at the end, and the proof is finished. Of course, we didn't have to carry that 3 with us. We didn't have to have that 3 in there. Having n equals 1 over epsilon would also work. Why? Because at this step over here, we could just forget about the 3. It would be better to do something like this. 1 over 3n is less than 1 over n. And now we can set n to be 1 over epsilon, and we'll get epsilon at the end, just like last time. So we actually don't even need the 3. Okay? Of course, if you want it to be really complicated, you could have set that expression, or you could have replaced the x with n right away in here and said that this part is less than 1 over 3n plus 2. And then you could have set that equal to epsilon and found the n which works. So in this case, if you were just to do some scratch work on the side, you'd see that 1 over epsilon has to be 3n plus 2. And that would imply that n would need to be chosen to be 1 over epsilon minus 2 divided by 3. Okay? That is a bit worse, because first of all, now we have to make sure that the n is in fact positive. So we have to make sure that 1 over epsilon is not too small. Okay? We could choose that value if the top happens to be positive and some other value of n in the other case. And then we would have n being equal to a maximum of 2 things. Okay? So this method is not the best. The best method is this one that I just wrote on the board right now. Okay? Where you simplify the expression as much as possible before even bringing n into the picture. All right? So that's that example. Let's do something just a little bit more tricky. All right, example 3. We're going to prove that the limit as x approaches infinity of this rational function equals a half. First of all, how did I know that that limit equals a half? Well, let's take a look at what we have here. The top is a quadratic function, the bottom is also a quadratic function, and we're dividing them out. Okay? Now, as x gets larger and larger, the top will behave roughly like 4x squared. Okay? This other stuff, this negative 3x plus 2, isn't going to make much of a difference to the value of the numerator if x is large. And if you want to see what I mean, substitute x equals 100 into the numerator. 100 squared is 10,000, times 4 is 40,000. So this part over here evaluates to 40,000, and then we're subtracting 300 and adding 2. The top is roughly 40,000. This stuff makes very little difference. Okay? So the top behaves roughly like a 4x squared. The other stuff doesn't really matter. The denominator behaves roughly like 8x squared. Again, the other stuff doesn't really matter. And 4x squared over 8x squared, the x squareds, you can think of them as canceling away, and you're going to have roughly 4 over 8 here, okay? Which is a half. So that's how I got that limit, and that's true in general. If you divide any two polynomial functions by each other, and they have the same degree, then the limit as x approaches infinity of that quotient is found by just dividing out the leading coefficients of the two polynomials, okay? In this case, 4 and 8. So, a little lesson of how to get the limit, okay? Now let's actually prove formally that this limit is a half. So, as usual, we're going to let epsilon greater than 0 be given. N is going to be equal to something, and x is going to be larger than n, okay? Maybe I should write here, be given, okay? There we go. And what we want to do is bound the function 4x squared minus 3x plus 2 over 8x squared minus 6x plus 1 minus a half. We want to bound that, make it less than epsilon. Step 1, simplify. That's always step 1, okay? 2 times this business minus 1 times that business, okay? The numerator, if we cross multiply, will be 8x squared minus 6x plus 4, okay? Then we're going to subtract away 1 times this, so 8x squared minus 6x plus 1, okay? Because there's a minus out here. And then that's going to be divided by 2 times 8x squared minus 6x plus 1, okay? So there we go, there's our expression. And now some stuff from the numerator cancels out. The 8x squareds cancel out. The 6x's cancel out. And what we just have is 3, okay? So the numerator is going to be 3. We might as well drop the abs value. We can pull the 2 out of the abs value in the denominator. So we have 2 out here, and then 8x squared minus 6x plus 1, okay? And now we want to say that this business here can be made less than epsilon, okay? As long as x is larger than n. So, what do we do at this step? It's sort of a little tricky. We have an absolute value, but there's a three-part thing inside. However, we know that that three-part thing eventually is positive, right? 8x squared minus 6x plus 1, that's just a quadratic opening up, okay? Eventually, once you go past both roots, this quadratic is always going to be positive. And we know that x is going off to infinity, okay? So we might as well drop the abs value and put in a little note to make sure that later, when we specify our value for n, we make n large enough, at least large enough, such that the quadratic actually is positive, okay? So at this step, let's just drop the abs value. We have 3 over 2, 8x squared minus 6x plus 1, okay? And we're going to put in a little star over here. We're going to come back to that step and make sure that it's justified, okay? But for now, let's work with this. Let's continue. So we have 3 over 2 times something. Now, we can drop the 1, as we did before, where we had 1 over 3x plus 2. We dropped the 2, right? And drop the 1, that makes the whole fraction smaller. Or rather bigger, because it makes the denominator smaller. So let's get rid of that pesky 1 there. We have 2, 8x squared minus 6x. Now, you might be tempted to also drop the 6x away, but you can't. Why? If you were to forget about it, we would make the denominator larger, which would make the entire fraction smaller. And so our less than sign would not be pointing in the right direction, okay? We would have this if we were to drop that negative 6x, which is not what we want to have. We want to have the inequality the other way, all right? So we cannot drop the 6x here. So how do we deal with that sum of two things in the denominator? Okay? Here, can't drop the negative 6x, okay? So beware. If you had a positive 6x here, we could drop that. But the negative, nope, we can't. So here's one technique of dealing with the negative 6x. We would like it to combine with the 8x squared, right? If that x was an x squared, this wouldn't be so bad, because we could combine these two together and then get a 2x squared in the denominator. Okay. So let's make the x an x squared. Let's say that this is going to be less than 3 over 2 times 8x squared minus 6x squared. It's almost like cheating, isn't it? However, it's justified. Why? Because as x gets larger and larger, the negative 6x squared is going to be larger than the negative 6x. Okay? And so here, when we replace this negative 6x with the negative 6x squared, we're subtracting more from the denominator, which makes the entire fraction bigger. Okay? So formally, what do we need for this step to work? For this step to work, to be okay, I'll write it like that. For this step to be okay, what do we need? We need negative 6x, we need that value there, to be less than negative 6x squared, okay? Or rather, to be greater than. I'll get the negative out of the way because it's confusing, okay? We need 6x squared to be larger than 6x, okay? This is what we need in order for that step to hold, right? We want to be subtracting more than what we were subtracting initially for the inequality to be pointing that way. Now, if 6x squared is more than 6x, the 6's cancel away, and what we're saying is that x squared has to be larger than x. And that's true whenever x is larger than 1, okay? So for this step to hold, for this step to be okay, we need x larger than 1, okay? Perhaps even equal to 1. Then we would have this, okay? But we definitely can't have x is smaller than 1. But that's okay, because x is larger than n, and we can just specify later on when we choose n that n is going to be at least 1, and then this step will work, okay? So, anyway, we've replaced the 6x with 6x squared. let's see what happens. This is equal to 3 over 2. Now these things nicely subtract away, and we get 2x squared inside here. Okay? And this is equal to 3 over 4x squared. Now, we can drop the 3 over 4, because why deal with it? This is, maybe I should write the stuff on this line here. 3 over 4x squared. We can drop the 3 over 4 and just say that this is less than 1 over x squared. And now, x squared is larger than x whenever x is larger than 1. So in fact, 1 over x squared is less than 1 over x. We can replace even further here. We can replace the x squared with x. And now we're ready to put in our statement involving n. So see how we simplify things as much as possible. Right down to get this, okay? Now, this is less than 1 over n, and that can be made equal to epsilon with the same choice of n as we had before. N had to be 1 over epsilon, okay? So let me just put that in, which equals 1 over epsilon, which is epsilon. The proof is done, and now comes the tricky part. We have to figure out what n is to be made equal to. So on the one hand, we do need the 1 over epsilon. We also need this, okay? We also need the x's to be larger than 1, which means n has to be at least 1. So from this step, this implies that n has to be larger than 1 or equal to, okay? This step here would imply that n has to be greater than or equal to 1 over epsilon, okay? And then the last thing that we forgot about is the star, okay? We drop the absolute value away. We do have to think about when exactly this is okay, right? So for x's being larger than 1, is this okay? Well, let's see. Where does 8x squared minus 6x plus 1 have roots? If you factor this, you get 2x minus 1, 4x minus 1, right? You multiply that out, 8x squared minus 6x plus 1, okay? So the roots here are at 1/2 and 1/4. After the half, this parabola here is always above the x-axis. It's always greater than or equal to 0, okay? In particular, when x is greater than 1, we're okay. And x is greater than 1. We chose n greater than or equal to 1. We're going to choose n greater than or equal to 1 to make x greater than or equal to 1. Okay, so this step is okay as long as n is greater than or equal to 1. Okay, so really the only things we need for this entire string of inequalities and equalities to hold is n greater than or equal to 1 and n greater than or equal to 1 over epsilon. Messed that up, didn't I? There's 1 over epsilon. Okay, and of course, if this is the case, then this equality that I wrote there before would change into an inequality, okay? So n has to be at least as large as 1 and 1 over epsilon, so we choose it to be the maximum of 1 and 1 over epsilon, okay? So just like in the finite epsilon delta proofs, we chose delta to sometimes be a minimum of two things. In this proof, we need n to be chosen to be a maximum of two things, okay? In these limit as x approaches infinity proofs, we often have these maximums. Another common thing that you see is the dropping of an absolute value, okay? Do this kind of thing as early as possible in these proofs because it makes everything simpler, okay? If you have several things in the denominator, drop as many of them as you can. The ones that you can't drop, you can replace with something else so that they combine. And of course, try to simplify everything as much as possible. At this step, we could have simply said that now 3 over 4x squared is less than 3 over 4n squared, and then chosen n to be the square root of epsilon times 3/4 or something like that. But of course, that looks a lot worse than just having a 1 over epsilon. So do simplify things as much as possible before you plug in your n statement, okay? So that's that example. There's no one way to do these limit proofs. In fact, you have perhaps even more freedom with the infinity type proofs than you do with the finite proofs. okay? So let's actually, before we move on, let's do this example in one more way. I want to show you one more technique. Approach number 2. All right? Second type of proof. Okay? I'm going to show you one more way of dealing with the negative 6x in the denominator if you didn't like the way I dealt with it before. Okay? So, as we've already seen, this thing simplifies to be, 3 over 2 abs 8x squared minus 6x plus 1. Okay? So that part with combining the two is the same. Okay? Here's where the difference will happen. Okay? We have 3 over 2 times this quadratic. Now we're going to factor the quadratic and see what we get. So keep the 3 and the 2 as is. And how does this thing factor? Well, we can factor into x, 2x minus 1? Yeah, 2x minus 1, 4x minus 1. Okay? There we go. We factored the quadratic. And now we can replace one of the factors with the other factor. So what's bigger, 2x minus 1 or 4x minus 1? It's the 4x minus 1. Okay? That's the bigger quantity. This is the smaller quantity. We can make the denominator smaller, which will make the whole thing bigger, by replacing the 4x minus 1 in abs values with a 2x minus 1. Okay? So this can be made less than, or rather this is less than, 3 over 2 times 2x minus 1 times another copy of 2x minus 1, so 2x minus 1 squared. Okay? And now when you square an absolute value, that's the same thing as dropping the absolute value and squaring whatever's in there. So this can just be written as 3 over 2 times 2x minus 1 in regular brackets squared. Okay, we don't need the absolute value in there. It went away on its own. Okay? Now to simplify this just a little bit further, we could actually take the 2 out of the bracket over here. Okay? So this will be equal to 3 over 2 times 2 squared, so 3 over 8. And then inside the bracket we'll have x minus a half squared. Okay? Now, the reason why I did that is because it allows me to now forget about these constants, right? Because here we have 3 over 8. We can just replace the 3 over 8 with 1 and say that this is less than 1 over x minus a half squared. Okay? And at this point, we're ready to introduce our n. Okay? Well, we don't have to introduce the n yet, but why not? Let's introduce the n. Let's say that this is now less than 1 over n minus a half squared. And now on the side, we're going to figure out what value of n we need to choose so that n minus a half squared is in fact going to be equal to epsilon. Okay, so on the side over here, or rather at the top, we want this equality. Okay, and now if we rearrange here, we get that n minus a half squared has to be 1 over epsilon, and that implies that n minus a half has to be 1 over root epsilon, and that implies that n has to be a half plus 1 over root epsilon. Okay? So at this step over here, we could say that this is now going to be equal to 1 over, and then we sub that value in. 1 half plus 1 over root epsilon minus a half squared, and that's going to equal to epsilon. So in fact here, we need n to be chosen to be a half plus 1 over root epsilon. Do we need another value of n? Do we need to take the maximum of any two things? No, actually we don't. This replacement was okay. This is always true. Okay? The squaring of the absolute value, this is always okay. We got rid of the absolute value that way rather than the other approach that we did where we just dropped it and then made sure the x's are large enough. Really the only thing we need to worry about a little bit is to make sure that x is larger than a half, because otherwise the x minus a half, if x is not larger than a half, if n is not larger than a half, sorry, then x could potentially be equal to a half, and then we might get boom down here in the denominator. Okay? But actually, the statement that we get, the value of n that we get, covers that case for us, right? N was set equal to be a half plus 1 over root epsilon, and that's always bigger than a half. So actually, we're all good. So no maximum statement in approach number 2. Okay? So just because you do a proof one way and there's a maximum statement doesn't mean that there always needs to be a maximum statement. This is a clever way to prove this statement, this limit, without invoking the maximum. Okay? Of course, if we wanted to simplify our expression for n a little bit more so as to avoid having that root epsilon in there, if you don't like the root epsilon, then at this step, we could have chosen to drop the square, okay? Another approach, so this can be approach number 3. At this point, we could have said that this was now less than 1 over x minus a half without the squaring, and then set that equal to epsilon. So replace first the x with the n, and then setting that equal to epsilon, you'd need n to be a half plus 1 over epsilon. So this would be 1 over a half plus 1 over epsilon minus a half. That would be equal to epsilon. But now, in this case, we'd need n to be a maximum of something. Of what? Well, we definitely need the half plus 1 over epsilon. But what else we'd need is, we'd need to make sure that the x's are big enough so that x minus 1, or x minus a half squared, is in fact larger than x minus a half. So at this step, we'd need x minus a half squared larger than x minus a half, or x minus a half larger than 1, or x greater than 3 over 2. So in fact, if we were to do this route, we'd have to also specify that n is at least 3 over 2. Okay? So there's yet another approach to proving this limit. A bit cleaner representation here because we don't have the root epsilon in there, but we do have a maximum. Sorry, this should be max here. Okay, max at that set. What is the best approach? This one looks pretty good. We do get a simple statement at the end for n, and we don't have a maximum in there. But if you can't think of this type of approach, because for a lot of problems, you probably won't be able to think of something like this. This just happens to work here for this question. Then the first approach that we did is pretty general. Okay, the replacement of the denominator, the negative 6x in the denominator, with something involving a squared. That's a much more general method that works often. Okay, so that approach would probably be superior to these two. Okay. Let's do one more example. So the last example we'll do today is the following. We're going to prove that the limit as x approaches negative infinity of x plus 3 sine x over 1 minus 3x. We're going to prove that that limit is equal to negative 1/3. Okay? Now before we do the proof, we need to talk a little bit about this. What does it mean for a limit as x approaches negative infinity of some function to exist? Well, the idea is very similar to approaching positive infinity, but a few modifications to the definition above here need to be made. So when x is tending towards negative infinity, the values of f are still getting closer and closer to L. Okay? F eventually falls within an epsilon window around L. Okay? However, we need to choose x's negative enough, okay, to make that happen. So the only modifications we need here for the definition of limit as x approaches negative infinity is we need to flip these inequalities over here. We need to come up with an n less than 0 such that whenever x is even more less than n, f of x minus L can be made less than epsilon. Okay, so as x gets smaller and smaller, or larger and larger in the negative direction rather, the function minus the limit is going to be less than epsilon. Okay? So now that we've made that modification to the definition, we can prove the statement. So let's go through the proof. Let epsilon greater than 0 be given. And we're going to let n equal something. And this something is going to be a negative value. And also we're going to let x less than n be given. Okay? So the n, again, will play the role of delta. It's going to be in terms of epsilon. But now we're going to have explicitly a minus sign somewhere in there in that expression, just to ensure that the n is in fact less than 0. Okay? So let's prove the statement. So we start with our x plus 3 sine x over 1 minus 3x. Oops, I forgot to subtract the limit. Minus negative a third, so that's plus a third, okay? We want to bound that above by epsilon. So let's start with the algebra, what we usually start with. 3 multiplies up there. Here we cross multiply, so we get 3x plus 9 sine x plus 1 minus 3x. And all that's going to be divided by 1 minus 3x times 3. Now, what happens over here is that the 3x's cancel out, and the top is just going to be a 1 plus 9 sine x. Let's just rearrange it a bit. 1 plus 9 sine x in abs values. This 3 comes out of the abs values, and then we have a 1 minus 3x in abs values as well. Okay? Now we get to the tricky part. So, the top is a sum of two things. Now, last time we saw that the sine x is bounded. Okay? We don't have a sine x alone, but we have a sum. So we can use triangle inequality to deal with the top here. Okay? So this can be made less than or equal to abs value of 1 plus abs value of 9 times sine x. The 9 comes out of that abs value. Abs value of 1 is just 1. So the numerator actually becomes 1 plus 9 abs sine x. Okay? And this is by triangle inequality and splitting of the abs over the product. And split abs over product. Okay? I really don't need to write this, but let's put it in. Now, what happens with the denominator? Well, we have a 3 here. Remember the standard thing to do with the infinity limit proofs? We would like to drop all the absolute values just to make things easier. Now, in this case, we have to consider what happens when we drop the absolute value. 1 minus 3x, it looks like it's negative, but actually this is a positive quantity. Why? Because x is negative. X is less than n, and n is negative. Okay? So in fact, 1 is positive, and then the negative 3x, we have negative times negative, that's positive. So in fact, we don't need to flip the sign or do anything here. We can just drop the absolute value right away, because this is always positive. Okay? So star here, 1 minus 3x is greater than 0 since x is less than 0. Okay? So with the negative infinity proofs, as x goes to negative infinity, we do have to be a little bit careful with the sign. Okay? All right, what happens now? Just like before, in the second example we did, we can replace the abs value of sine with just a 1 and get rid of it entirely. Okay? The sign, whenever you see a sign in an example where x is tending to infinity, usually it's just put there to screw you up. Okay? You're expected to notice that you can just forget about the sign and replace it with 1. All right? So don't let yourself fall into the trap of worrying about the sign. Just replace it with 1 and have it over with. So this is less than or equal to 1 plus 9 times 1. So 10 goes in the numerator. And then in the denominator we have 3 times 1 minus 3x, okay? Which, by the way, is just equal to 10 over 3, 1 minus 3x, okay? Now we're ready to simplify a little bit. We can remove the 10 over 3, okay? 10 over 3 is just 3.3, all right? We can just replace that with a 4 in the numerator. Like, why not, right? Why have a 10 over 3 if you can have just a simple 4, okay? Over 1 minus 3x. And now, we need to deal with this. So, first thing we notice is that we do have a positive 1 here. This quantity is positive. But because the 1 is positive, it's being added into the denominator. If we remove that 1 away, we are making the denominator smaller, a smaller positive, which makes the entire fraction bigger. So we can remove the 1 and just have this to be 4 over 3x. Okay? And now we can simplify things even more by getting rid of the 4/3 and replacing that with, say, something like 2. I mean, why not? Why have a 4 over 3 in there if we could just have a 2? So this is now less than 2 over x. Okay? Now, I did make a little mistake here. I forgot about the negative, which is very important. Okay, sorry about that. This 2 over negative x quantity is positive. Okay, and now we're ready to introduce our n. So x less than n is given. So what do we know from this statement? From here we know that x is less than n. That implies that 1 over x is greater than 1 over n if we reciprocate. Okay? Of course, 1 over x is less than 1 over n in absolute values, right? X in absolute values is greater than n, but this inequality is pointing the other way because these are negative numbers. So, let's multiply through by a negative, make both sides positive. We have negative 1 over x is less than negative 1 over n, okay? These are now positive numbers. We can replace that negative 1 over x here with the negative 1 over n. So at this step, we can simply have this will be a less than negative, or rather, yeah, sure. Let's put the negative in the 2. No, let's keep it on the n. 2 over negative n. There we go. And now we're ready to equate that to epsilon. Okay? So this can be made equal to epsilon, and the proof will be done as long as we choose what value of n? Negative 2 over epsilon. So here we need to pick n equals negative 2 over epsilon for this to work. Okay? Let's throw that in there. So n is chosen to be negative 2 over epsilon, and now the proof works. So let's put down the square. That always feels good. Put the square in there. And we actually don't need a maximum or anything like that. Okay? So the trickiest part of this argument really is the fact that we're going to negative infinity. Okay? We do need to pay attention to the signs here. Even though x and n look positive, they are in fact negative numbers. And therefore, when you see an explicit negative in front of them, that actually means we have a positive number. Okay? That's why we have this funny little inequality here, where negative 1 over x is less than negative 1 over n. And then, of course, when we actually pick our n value, we have to make it a negative number. So n always depends on epsilon in these proofs. As we go to negative infinity, we have to put in somewhere an explicit negative sign. Or we have an epsilon expression which actually evaluates to be negative if we happen to have, if we pick any positive epsilon and put it in there. Okay? So in this case, we do have that explicit negative. And there we go. There's the proof. Now in a future video, I will talk about properties of limits at infinity. It turns out we can transform a limit going to negative infinity problem into a limit as x goes to positive infinity. And then we could do our proof in the usual way without worrying about the funny inequalities and the negatives in there. Okay? But that's for another time. For today, this is the proof. This is how you use the actual x going to negative infinity definition and do a proof of a limit from first principles. Okay? Thanks for watching.